Up to this point, we know that graph convolutions are permutation equivariant, and that this property is inherited by graph neural networks. Basically, permutation equivariant says that when we take a graph filter and use it on a given shift operator or on a permuted version of that shift operator, nothing changes. But what happens to the output of a graph convolution when they are subject to more generic changes of the underlying graph support? In this segment, we will discuss the model of absolute perturbations, and we will show that graph convolutions using Lipschitz graph filters are stable to absolute changes in the support. Consider a graph with a shift operator S and another graph with a different shift operator S hat. Consider a set of filter tabs HK that define filters big H of S and big H of S hat based on S and S hat respectively, but with the same filter tabs HK. What we want to do is to characterize how different are H of S and H of S hat for the given shift operators S and S hat and for the same filter tabs HK. What we know is that if S hat is a permutation of S, then the output of the filters has to be the same. What this suggests is that we want to measure the distance between filters so that it is measured modulo permutations. Essentially, we compute the operator norm between the filters, finding the permutation of one of the shift operators in such a way that this norm is minimum. This gives us the distance between operators modulo permutations. Now we can measure distances between graph filters modulo permutations. What we want to do next is to characterize this distance between graph filters as a function of some distance between the supports S and S hat. That is, we want to know how changing the graph support affects the output of a filter. To measure the distance between S and S hat, we consider the set of absolute error matrices. This is the set of all matrices E such that when added to the shift operator S, they yield a permutation of the shift operator S hat. The absolute perturbation distance between the shift operator S and S hat can then be defined as the norm of the matrix E with the smallest operator norm among all matrices E in the absolute error matrix set. To quantify the effect of the shift operator on the output of a graph filter, we will proceed with an analysis in the frequency domain, a trademark of signal processing. Recall that the effect of a graph convolution in the frequency domain is to rescale the ith frequency coefficient tilde x sub I of the input by a corresponding value h of lambda sub I given by the filter and the ith eigenvalue of the support, yielding the ith frequency of the output tilde y sub I. In particular, we will restrict our attention to the class of Lipschitz filters. Lipschitz filters are those whose frequency response satisfies that their derivative is bounded by a constant c. The plot shows an example of a Lipschitz filter. The main theorem of this segment states that graph convolutions are stable to absolute perturbations. Given two graphs with shift operators S and S hat respectively, such that their absolute distances are smaller or equal than epsilon, then Lipschitz filters with constant c satisfy the following. The difference in the output is bounded linearly by the distance between shift operators. The bound depends on the filter through the Lipschitz constant c and on the perturbation model through the eigenvector misalignment constant delta. The constant delta depends on how different are the eigenvectors of the shift operator S and that of the perturbation E. Knowing more about the perturbation E will certainly allow to compute better values of delta. In any case, this constant is always bounded by 8 due to the unitary nature of the eigenvector matrices. We emphasize that this bound is universal for all graphs with the same number of nodes n. The next logical step will be to discuss how to extend this result from graph convolutions to graph neural networks. However, doing so in this context is pointless. And this is because, while the theorem is true, and it does hold for all graphs, it is actually not very useful. And it is not very useful because the absolute perturbation model is useless. It is way too arbitrary. Absolute perturbations link S hat with S through an error matrix E following the sum. The problem is that this matrix E can be arbitrary. To better explain this point, consider a stochastic block model with two communities given by S1 and S2. Suppose that the second community is more weakly connected than the first community. We can increase the connectedness of each block by increasing the edge weight, and the resulting graph will still show a community that is half as weakly connected as the other. However, for the same price, that is, for the same error norm, we can completely alter this structure and end up with two communities that have the same connectivity. Consider again the stochastic block model with two communities for an even more striking example. We can increase all edge weights by the same amount. But for the same price, we can completely ruin the stochastic block model by adding connections between nodes that were not connected before. What these toy examples actually show is that the absolute perturbation model lets us alter the graph topology arbitrarily without changing the price to pay. So, in essence, yes, we could extend stability to absolute perturbations from graph convolutions to graph neural networks. But it is kind of pointless to do so in the context of absolute perturbations. What we actually need to obtain a meaningful stability result is a better perturbation model. That is one that takes into account the topology of the graph being perturbed.